All right, so today we're covering the 9.1 material. We're going to get into 9.2 shortly after it as best we possibly can. But we're working with exponent properties with products. Like, essentially just think of these as exponent properties with any and all kind of exponents that we're going to be working with. Now I'm going to go through a few examples primarily with this first section because there are some very subtle points with exponents that absolutely need to be clarified before we move forward with them. And the main one with that is recalling that an exponent takes a base, should be and in here, and multiplies it by itself a number of times equal to the exponent's value. So the big part that I'm going to emphasize with this, and we see it in a couple of the examples here, and I'm going to go through a few of these over on the whiteboard right now, just for the sake of seeing it, because it's important to see, is that when we are working with exponents, whether it be in this capacity or a different capacity, whatever it may be, the biggest challenge that I see that people have to face is what is the base of the exponent? And this primarily comes into play when we have a mix of positives or negatives or parentheses or no parentheses as we're going through these types of problems. So the first set of examples that we had, I'm going to do some slight variations on it because I think it's worth just pointing out some of these. So we're told to expand and simplify. And when you're going through problems with exponents on the homework or on the test, and I'm just telling you guys to simplify or evaluate, you do not need to do all of these steps. If you can plug in your calculator or do it in 1 or 2 lines of work, that's fine also. But the idea of expanding an exponent. So our first example that we had, we were working with 3 to the 4th. Make that a better 3. That looks terrible. There we go, a bit better. So we want to expand and then simplify. So we always need to make sure that we are correctly identifying the base of the exponent and what the exponent itself is. So the exponent itself is the number 4 in this problem. The base is the number 3. So expanding this out, 3 to the 4th is saying 3 times 3 times 3 times 3. So it's writing that out 4 times. And then we can go through and actually multiply each of these things together and simplify it down. The first 2 3s, 3 times 3 is 9. 9 times 3 is 27. And then 27 times 3 is 81. So we get 81 for our final answer. And again, this is just for seeing if we are told expand and simplify. So we expand things out in our second line of work, and then we bring it all together for our last one. Now I'm going to slightly deviate from the notes we have here in terms of our examples, because I do want to show 3 of them in a specific way here. So we're slightly different from the notes here, but let's say we have 5 squared. So again, we have something raised to a power. We need to correctly identify the base and correctly identify the exponent. Well, the base in this instance is going to be the number 5. It's the only thing that's being raised to the second power. So expanding that, I'm taking the base times itself twice. And then 5 times 5 is going to give me 25. Ooh, okay. There we go. Now again, I want to draw the comparison here because this is where we start to see the interesting stuff show up. Negative 5 squared. Now this is where a lot of hangups happen. It's understandable because there's some subtle stuff that's going on here. What is the base of the exponent in example 3? And this is where the tricky part comes in. A lot of people will say, well, it's the negative 5. It's the negative sign and it's the 5 that shows up. And it's not an unreasonable assumption to put those two things together as being the base. Nothing wrong with that. However, before we go through and solve this one, I'll set up our final and a contesting one here with this. We have the quantity negative 5 squared. So in our, I'll write this in here, our fourth example, come on, Screen's being a bit weird for me here. With our fourth example, we have the quantity -5 squared. Now, examples 3 and 4 look extraordinarily similar in the sense of, well, it's a -5 and there's a squared, but one has parentheses. And should that really matter with identifying the base? And yes, it absolutely does. In example 3, we're having -5 to the second power. That means the only thing that is going to be affected by this exponent is just going to be the number 5. The negative out front is just going to be along for the ride as we're going through this. So we have a negative, and I'm expanding the base. So the base of the exponent number 3 is the number 5. Example 3 is number 5. So the base is 5. It's being raised to the second power, and I expand it out to be -5 times 5. And 5 times 5 is 25. The negative out front is just going to stay there. It's just along for the ride. And we get -25 for our final answer. Now in the last example, we have number 4 over here. It's the same as saying, okay, well, what is being raised to the second power? Again, we need to correctly identify the base with all these exponents. And I know this, I'm spending an extra amount of time on this, and maybe for you, you're listening to this going, okay, it's obvious, I get it, I can't stress it enough how imperative it is that you correctly identify the base of the exponents now and moving forward. So the base in this instance, we have a parenthesis being raised to the second power. It's the big difference between number 4 and number 3. Number 4 tells us everything that's inside here is being raised to the second power, which means the base of the exponent, or number 4, is going to be -5. And I'm going to expand that as I write it out. So then I get -5 times -5. That's going to give me a +25. I have the final answer. Okay. So again, it's one more example than what was originally listed on the notes. But again, I wanted to emphasize the difference between these 3 scenarios. Something raised to a power, a negative something raised to a power, and then a negative number being raised to a power. And again, these two examples 3 and 4 are the ones that are most commonly misconstrued, I think we could say. A lot of people think these are interchangeable, and they get, you can do whichever one because you'll work with them the exact same way, and da-da-da-da. Well, it's not the case. And if you want to go off of the idea of, well, it doesn't matter and who cares, put a couple zeros at the end of this number, put a $sign in front of it, and that's your bank account. You want -$25,000 or a positive $25,000. It's kind of one way of looking at it. So make sure, again, when you're going through this entire section, whenever you're working with exponents, correctly identify the base of the exponent you are working with. If you do not do that, all of this will fall apart. Everything in Chapter 9 would fall apart. Everything in the future problems that you're doing is going to fall apart. It is absolutely critical. All right, so the final example that we had from that group was working with, I guess it's technically example 5 now. We are working with y to the third power. So again, we're told to expand this thing. So we need to correctly identify the base of this exponent. So I have y being raised to the third power, so I'm expanding out and having y times itself 3 times. So we've expanded this thing, and if we attempted to simplify it, which we technically could do, it would condense right back down to being y to the third power. And I believe there might be 1 or 2 problems that are going to have you do something like this on the homework, expand or simplify or write something in expanded form. Because that is what they're asking for, this is a perfectly reasonable answer to have. Y times y times y. We're just expanding that base based on what the exponent's value is. And there's not much else to it in that regard. Okay. I'm going to jump us back over to our notes, and we'll get going on the actual rules that we have for working with exponents. So our first rule that we have, I'm going to go through each of these two rules, and then we'll go through the examples, because I think it's nice seeing all of these at once instead of having to flip back and forth. So our first one that we have is the product rule for exponents. It tells us that when two exponential expressions multiply together and the bases are identical, should just say are identical, the exponents will add together. And again, there's a very subtle but extraordinarily important piece of wording that's in there. The bases are identical, which means as we are going through these, you need to make sure you are once again correctly identifying the base of each exponent that you are working with. If you are not doing that, you are going to get wrong answers. So if the bases are the same and they are multiplying, add the exponents together. So our general form of writing that out, just a general equation with it, we have x to the m times x to the n. The base of both exponents is the same, it's both x. And that means that when I'm going to simplify this down, I do not need to actually expand it like we did up here. I can just add the exponent values together. So my result will end up being x to the m plus n. And we are assuming m and n are non-zero numbers in this instance. So I have x to a value times x to a different value. I can just add those two exponents together, get my final answer. And we'll go through a couple examples of this. I'll show one of these expanded out just because I think it's worth seeing once. But we'll get to these here in a second. The other rule that we have is the power rule. So the power rule tells us that when raising an exponential expression to a power, the exponents will multiply together. And we have two instances of this that will show up. We have just one base or one exponential expression raised to a power. So I have x to the m raised to the n power. And again, exponent being raised to a power, the exponents will multiply together. So my result is going to be x to the m times n power. And again, m and n will be represented with numbers, and we can just multiply them together as necessary. The other instance that we have is a product being raised to a power. So here we're starting with x to the a and times y to the b, all raised to the n power. So similar idea, x to the a raised to the n, we can multiply those exponents together. So I get x to the a times n for my first expression here, my first base. Working with y, similar idea. I have y to the b raised to the n, so the exponents are going to multiply together. And I'll get y to the bn. And because everything originally was multiplying together in here, I'm going to have my result have everything multiplying together in here. So I'll have x to some exponent times y to some exponent, and then we can go from there. So I will show an example of this, but this is also, we can see this played out when we are expanding out the base of an exponent and then bringing everything together. So the power rule is basically an expansion on the product rule. And it gives us some quick ways of going through and speeding up the process, as it were, for going through these. So I'm going to jump us over to the whiteboard, and we'll go through some of these examples, just because I want to give you guys the opportunity to see how it works both ways when you're simplifying these out and how these do relate together. So we'll jump on over there. And, oh, not what I wanted. I just want to move this thing. There we go. Okay, so we're going to simplify some of these down. And again, we're going to be mixing from the examples from the product rule and mixing examples from the power rule we have in there. So our first one that we're working with, we had n to the third times n to the fifth. Now I'm going to show this. This is using the product rule, but I do want to expand it out just for the sake of seeing why we use these property rules, because it just speeds up so much time for us. So let's say we're going to simplify this using the previous method that we did above, where we expand everything out and then simplify things down. So I'm going to go through it once because it's a painful process, but let's write that out. So our first set of parentheses has n to the third power. The base is n, the exponent is 3, so I'm going to have n times itself 3 times. The second expression has n to the fifth power. The base is n, the exponent is 5, which means I'm going to have n times itself 5 times. Now, when we are multiplying these things together, going back to our product rules, we're going through this now. The bases are the same. They are all multiplying. And now in this expanded form, I'm seeing that n is multiplying by itself 8 times. We can count that up if we wanted to. We've got 1, 2, 3, 4, 5, 6, 7, 8. So I can condense this thing down then to being n to the 8th power. Okay? So this is using our expand and then simplify method. This is mostly one that you can use it if you want to, but using the actual products, the properties makes life a lot easier on that front. So we're going to go through, I'm just going to show you guys the same problem, but using the product rule. So again, we're starting with n to the third times n to the fifth. So I'm looking at these and saying, all right, the bases of the exponents are the exact same. The base is n for both of them. If the base is the same and they are multiplying together, then I can add the exponents together and simplify from there. So really, I have n to the 3 plus 5. 3 plus 5 is going to give me 8, so I get n to the 8th power for my final answer. And again, when you are going through these on the homework, when you're going through these on the test, you do not need to expand and then simplify like we did in the first go through this example. You are welcome to, but you'll see with some of these exponents, the numbers and the amounts of them get really, really big, and it's going to eat up a lot of space. So use these properties that we have. They're shortcuts. It's exactly why I'm giving them to you and why we want to give them to you guys. Make your lives easier as best we possibly can. Oops. There we go. So our second example from the first set, we have 2m times 5m to the third. Now we're throwing in some extra stuff in here, but that's fine. We now have numbers and we now have variables. And my recommendation to you is do these in parts. Say, all right, I'm going to work just with the numbers. I have 2m times 5n cubed, just looking at 2 and 5. 2 times 5, that's going to give me 10. My numbers, done. Now looking at my variables, I have m times m to the third. Remember that if there is nothing explicitly written, it is implied that there is an invisible 1 as the exponent for that variable. So technically, I have m to the first times m to the third. The bases are the same. They are multiplying together, which means the exponents are going to add together. So really, I have 10 to the m, or 10 times m to the 1 plus 4. 1 plus 3. Gosh. Spoiler alert there. And when I do add those together, then I'm going to be getting 10m to the fourth. That's going to be your final answer. Take a look at let's take a look at number 4 from that first set, because I think that's a better one to take a look at here before we go on to the others. So number 4 from that first group of examples, we are given negative 2xy squared times 8 x to the third y to the fourth. Now again, we've got a multitude of things that are going on here. We've got numbers, we have x's, and we have y's. So again, I'll emphasize this. Do not try and do all of this at once. Work with it in parts. Let's work with the numbers first. I have -2 times 8. It's going to give me a -16. So my numbers, done. Now I have two variables. I have x's and I have y's. Doesn't matter which one you want to go with. Just pick one and move forward with it. I'm going to choose the x's first. Excuse me. I have x to the first times x to the third. So if the bases are the same and they're multiplying, the exponents add together. I have y to the second times y to the fourth. The bases are the same. They are multiplying. So it means the exponents are going to add together. When we do that, we're getting our answer of -16, x to the fourth, y to the sixth. And then this intermediate step that I have written in here, if you were able to do the calculations for the exponents in your head during that time, you're welcome to do that. I just want to emphasize how we're using the product rule here for these. Okay. Now it'll jump us to our next set of examples that we had. And this was working primarily with the power rule. Separate this out here. So we're applying the power rule for these ones. And again, very similar to our previous examples, we're just applying that property. So for this set, our first thing we're starting with is x to the third raised to the second power. And again, I want to show you guys where we are getting this power rule from. So I'm going to show you guys how we solve it with expanded form first. We're expanding it out, and then we'll go from there. So what is the base of this exponent? Well, we have x raised to the third power, so x is the base. And then we have everything inside a set of parentheses being raised to the second power. So that's also a base. So if I were to expand this thing, expand and simplify, everything in the parentheses is multiplying by itself twice. And now I have x to the third times x to the third. That's exactly like what we were just doing in the examples above. The bases are the same. They are multiplying, which means the exponents are going to add together. We get x to the sixth. So this is using our expanding and simplifying method, if you want to call it that. So now we'll do it with the power rule. Let's do that. So again, same problem. X to the third raised to the second power, better 2. So I have an exponential expression being raised to a second power. Based on our notes that we have, all I'm going to be doing is multiplying these exponents together. So I'm going to have x to the 3 times 2. 3 times 2 is going to give me 6, so I get x to the 6th power. And we have our answer there. Not a whole lot to it on that front. So we'll take a look at our second example from that set, where we're given 4a to the fourth, 4a to the fourth raised to the third. Getting ahead of myself there. So just like we did before, except now we have a product being raised to a power, which is fine. We're taking each of the bases of the exponents inside the parenthesis, and we're going to raise those to the third power. So that 4 has an invisible 1 out front of it, or hanging out there. So it'll be right up there. So I have 4 to the first raised to the third power. And again, the exponents are going to multiply together here. So really, I have 4 to the third power. I have a to the fourth raised to the third. Again, whenever I'm raising an exponent to a power, the powers are going to multiply together. So I'm going to get 4 times 3. Our next line of work, 4 to the third power, I believe that's going to give us 64. You can apply your calculator for that if you need to. And then 4 times 3 for the exponent of a is going to give me 12. And I have the answer there. And we'll take a look at, we'll take a look at one more here before we move on. I want to make sure we have a good number of examples under our belt. So number 3 has us working with 3a squared b, all raised to the third power. So again, when we're going through these, we need to correctly identify the base of the exponent. And in this instance, the base of this 3 on the outside is everything inside the parentheses, and that does include the negative sign in there. So just like we did with our previous example, I'm going to work with this in parts. I'm going to work with the numbers, then I'll work with the a's, then I'm going to work with the b's. So I'll show you guys using that same idea, another way that some people I've seen in the past try and organize their work. And I'm fine if you want to use it. It's pretty helpful, I think, but it's your choice and if you'd like to do it this way. So because I have numbers, a's, and b's, I'm going to work with each of them individually. I'm saying I want -3 to the third power. I want a squared to the third power. And then I want b to the third power. So you could write it in this form as well, because everything is inside of parentheses. So now, again, we're just doing it in parts. -3 to the third power. That's -3 times -3. It's going to give me 9. Times a final -3, which is going to give us -27. You could also apply your calculator there. We have a squared raised to the third power. Again, by our power rule, exponents raised to a power multiply together. And the same idea for our b value. It's the same as saying b to the first raised to the third. It's going to be b cubed. There we go. And there is our final answer. So again, I cannot emphasize it enough when you are going through these problems. Correctly identifying the base of the exponent is absolutely critical. And what's nice about having these rules, these properties that go along with them, is they save us time from having to write things out in all these expanded forms. Kind of like what we did, with our first examples up here. Every single one of these problems that we just did down below, you could expand all of these out if you wanted to. You're going to use a lot of paper doing that, but use the properties also to make your life a bit easier in terms of how much we have to write out. And again, if you are doing that, take the extra 10 seconds, 20 seconds to correctly identify the base of each exponent. Because again, if you do not do that, all of this falls apart. I can't emphasize it enough. I really can't without it. Basically, I'm going to lose my voice if I do that. Okay, so I'm going to jump us back to our notes because we're going into the second part of 9.1. This is an introduction to polynomials, which we're going to see quite a bit of moving forward now. So we have a couple definitions that we need to go through first. First, we have terms. So a definition of a term is a number or a product of a number and one or more variables, which may be raised to different powers. So essentially a term, I think we went through this earlier in the quarter, if we have variable terms, we have constant terms, things of that nature. So a term can just be, again, just a number or a product of a number and one or more variables. So we have number 14, 8x is a term, m is a term, Negative 2t squared is a term. Again, it's all multiplying. Negative 3x cubed y to the 6th. This is all a term because everything is multiplying. So definitions of having terms. Quick examples with that. So then we get into the expanded version on that when we start to add or subtract these things together. And this is where we get polynomials. And a polynomial is a term or sum of terms in which all variables have whole number exponents. Basically a fancy way of saying I have a bunch of these different terms that are adding or subtracting together. And again, a polynomial can just be a single term right there of 4 or a single term of 9x. We start to see this play out a lot more when we have instances of something like this, where we have two terms. We have 2m minus 4. I have the term m. I'm subtracting the term 4 from it. We can have bigger ones, or we can have 3 terms adding together. And even larger, we can have 4, or 5, or 6, or 10, or 100, or things like that. So a polynomial, again, is a term or a sum of terms, which all variables are whole number exponents. This is just some vocabulary that's thrown in here too, because it does get thrown around quite a bit, but I want to clarify it. Within the overarching umbrella that is a polynomial, we have 3 primary classifications that we have with these. I want to go through these because these are the most common ones that we see, and they show up fairly regularly on the homework or on tests or anything like that. So a monomial is a polynomial that only has a single term. That could be an instance of having 4 or 9x or 8x or m or negative 3x cubed y to the 6th. It is one single term, that is it. A binomial is a polynomial with exactly 2 terms. So that could be the instance of 2m minus 4. It could be x plus 1, a minus 13, but it only has 2 terms in it. And then a trinomial is just an expansion on the binomial one. It's a polynomial with exactly 3 terms. So that could be 6x squared plus x minus 2. This whole thing could be classified as a trinomial. We do have names for polynomials that are greater than 3 terms, but you really do not need to know them. You do not need to go out and learn and memorize them. It's a waste of time if you want to do that for what we're going to be working with. So we have the overarching idea of polynomials, and then we have these 3 main subclasses of them that we work through for the most part. Okay. So our next parts that are coming up with this is the idea of the degree of a polynomial. So if I'm asked you, I'm given some polynomial, it could be a monomial, binomial, trinomial, who cares? The degree of the polynomial is the same as the degree of its terms with the largest degree or exponent attached to it. So looking at our examples that we have up here, if I am being asked, we'll work at our sets down here. If I'm being asked what is the degree of 2m minus 4, our answer is going to be 1. The same as the degree of its terms with the largest degree or exponent attached to it. So between 2m and 4, the largest exponent that I have here is 1, and m to that invisible 1 power that's up there. So the degree of this particular polynomial is 1. I'm looking at our trinomial here. What is the degree of 6x squared plus x minus 2? The degree in this instance is going to be 2. It's the same as the degree of its term with the largest exponent. So the degree of this thing is 2. Looking at our last example, what's the degree of this whole thing? And again, it's the degree of the largest term with, or the term with the largest exponent attached to it. So the degree of this variable is going to be 3. Again, just some buzzwords, terminology, and examples that we have here with this, but these are all worth going through. So we'll get into evaluating polynomials, which we did actually a fair amount of earlier in the quarter. So I'm going to give a quick refresher on this, and then we'll maybe go through one example or two. But if we have been given or asked to evaluate polynomials, we plug in values for the given variable or variables as specified in the problem. I'm going to jump us over to our examples with this. So this should look very, very similar to stuff that we did earlier in the quarter, except now we have exponents thrown into it. I have been given, in our first example, 4x plus 7, and I want to evaluate that for x equals 6. So all that means, wherever an x shows up in this problem, I'm plugging in 6 instead. So x gets plugged in here, or 6 gets plugged in for x. 4 times 6 is going to give me 24. 24 plus 7 is going to give me 31, and I have my final answer. Evaluating it from there is just using PEMDAS. Looking at our second example, if we're told evaluate this polynomial, we have to be given a polynomial, which we have, 3x cubed minus 6x squared minus 9, and we are evaluating that for x is equal to 2. So anywhere an x shows up, I'm plugging in a 2 in its place. And again, when you are substituting values in, put them in inside of parentheses. So I get 3 times 2 to the third power minus 6 times 2 to the second power minus 9. We can plug this into our calculator. We can use PEMDAS. This is all stuff that we've done earlier in the quarter with how to simplify it from here. But the big difference is starting from a polynomial, plug in the value or values that we've been given for their corresponding variables, and then we evaluate. And then we have group problems. These are challenge problems that normally we go through in class, but we are not in a classroom right now. So if you want some additional practice, here's a little bit more challenging stuff if you want to do that on your own outside of the book problems. But this is all of the 9.1 material. I'm going to jump us over here. We're going to start working on the 9.2 material. See how much we can get through, and if we need to get through the rest of it tomorrow, then we'll do that. But 9.2 has us working with adding and subtracting of polynomials. So again, we wanted that definition of what a polynomial is before we get into this. So again, I'll move us back up here just to show those again. So again, for our polynomials, the main classifications that we use, and you'll see these terminology, these words thrown around pretty regularly, a monomial, a binomial, and a trinomial. Anything bigger than that, we just refer to it as a polynomial. But we're working with all of these types of expressions. So first and foremost, when we are working with addition and subtraction, we want to have our answers in what we refer to as standard form of polynomials. So after a polynomial expression has been fully simplified, it must be written into standard form using the following guidelines in this order. So if, let's say we're getting a little bit of our head out of ourselves with where we're at here, but we're going to follow the hypothetical. I have two polynomials that I've just added together. Great. It's all simplified on that front. We then need to make sure that we have ordered this polynomial into being in standard form. So the way we do this, we have a bunch of terms that are written out for us, and we need to write them first in alphabetical order, and then by descending powers or degree of the entire term, meaning all exponents added together to be the degree of that term. When we are doing this, the coefficients have no impact on rewriting the polynomials into standard form in any way, shape, or form. The only thing that dictates how I'm going to move these things around is what are the variables and what are the exponents attached to those variables. So we'll go through our first two examples that we have here. We want to write the following into standard form. So I'm starting with y to the third minus 7z to the fourth plus 2x. I cannot simplify anything down for this expression. I cannot do any addition, subtraction, multiplication, or division. So I just want to reorganize this into standard form. So first and foremost, alphabetical order before anything else. I have y's, z's, and x's. The x's automatically need to go out front because, again, alphabetical order. So when we do that, we keep the number, the sign, and all of that clumped together. So this 2x, which is positive, is going to be going out front, just like we have it here. So now I have the alphabetical order of x, y, and z. I don't need to worry about descending powers because each of these have different letters attached to them, so we don't need to worry about that second step in the process, and we're good here. So we have this thing now written in standard form. Looking at our second example, we have 10xy minus 5x cubed y to the fifth plus 9x to the ninth y squared. So again, writing this into standard form. First and foremost, alphabetical order. Well, all of these have xy in them, so I can't really go off of alphabetical order, which is fine. This happens. So now I need to go by descending powers, well, the descending degree of the entire term. So we're looking at this saying, okay, well, which term has the highest degree to it? And the way we figure that out is if I were to add all the exponents together, which one has the highest degree attached to it? Looking at our first one, xy. These have invisible ones for the exponents, so the degree of this term is 2. Looking at our second term, x cubed y to the fifth. If I added those together, that would be a degree of 8. And lastly, I have x to the ninth y squared. If I added those together, that would be a degree of 11. So by descending powers, so this x to the ninth, y to the second is going to go out front. It has the highest power to it, or highest degree. The negative 5x cubed y to the fifth is going to come directly after it. It's the second largest in terms of its degree. And then 10xy is going at the very end because it has the smallest degree, or smallest amount of powers that are attached to it. So we're just reorganizing it in this instances. Again, the coefficient stays the same. It has no impact on how we're working through these. And we just need to make sure that we're keeping any and all the signs in front of them the exact same as we move these around. So I'm going to take a quick look here at what we have for the rest of this. That's what I think it is. Yeah. So the only major difference that we have now in terms of addition and subtraction with polynomials, when we actually get into this, we just add and subtract them together as if we were combining like terms. And we've done this like we did in 3.4. Nothing is really changing in our process for it. The only difference, and I wouldn't even say it's a difference, the only thing I will try and reemphasize is be sure that you track any sign changes that take place from the distributive property. So if you are distributing this negative through, you are making sure it affects both the 4y and the 4. If you're distributing this negative through over down here, this negative is going through to the 2x squared, it's going through to the negative 8x, and it's going through to the positive 4. Make sure everything is included in this correctly. But otherwise, the only difference that we have is at the very end, you need to write your final answer into standard form. Everything else with adding and subtracting these things together, we have already done. The 3.4 material all over again. So if you need to go back and reference the video, if you need to go back and reference the notes for it, absolutely do that, because there really isn't anything that's going to be changing about this. And again, if the numbers get a bit gross with adding them together, use your calculator. That's totally fine. Nothing wrong with that. Okay. So this is everything for the 9.1 and 9.2 material. The only thing left on the 9.2's second page is just examples of going through these, if you would like some additional practice for going through that. But again, nothing is really changing in the process. We're just adding and subtracting, multiplying these things together as if we were combining like terms. Nothing special about it. Or nothing new, I should say, that's special about it. So I'm going to end us there for today for the recording, and then I'll take any questions that you guys have directly after.